May 29th, 1943. Headquarters, Oberkommando der Marine, Berlin. The air in the conference room was thick with cigar smoke and the scent of defeat. Admiral Karl Dönitz, Commander-in-Chief of the German Navy, paced before a massive map of the North Atlantic. For 6 months, the U-boat war, once on the cusp of victory, had devolved into a catastrophe. In the first 3 months of the year, 41 U-boats had been lost. In May alone, the number had reached 43, a crippling 25% of the operational fleet. U-boats were simply vanishing, stalked by a phantom enemy they could neither see nor hear. The veteran commanders of the wolf packs called it the Night Hunter, a silent executioner that struck from the overcast sky. What none of them knew was that a piece of captured technology, now laid out on a table in an adjacent laboratory, was about to expose the profound technical superiority that had forced the Kriegsmarine to fundamentally alter its strategic operations in the Atlantic. The Allies had owned the night skies over the convoys for over a year. Since the introduction of the 20th Escort Group, with their very long-range aircraft in 1942, Allied air patrols had run their routes with near-total impunity. German submariners had nicknamed the Allied aerial supply routes the Iron Scythe, and it had become the executioner cutting the lifelines of the U-boat fleet. The Allies' technical superiority in night operations had been demonstrated catastrophically at the Bay of Biscay in March, where British aircraft sank 7 U-boats in 8 days. Their new airborne radars could strike targets at a range of 25,000 yards. Their crews had trained for years in coordinated night attacks. Their optical equipment and trained radar operators could spot a surfaced U-boat in near-total darkness, where German surveillance efforts often failed. Grand Admiral Erich Raeder's earlier strategy had been straightforward: control the surface and subsurface, control the choke points, control the supply lines, maintain the pressure. The British might own the daylight skies with their shorter-range fighters, but darkness and the open ocean belonged to the Kriegsmarine. Without the nocturnal surface attacks and submerged transit routes, the U-boat offensive against the convoys would collapse within weeks. The captured radar set represented British industrial ingenuity, pushed to practical limits. Dr. Arthur Seyss-Inquart, the head of the FuMB section, had received the recovered components from a downed short Sunderland flying boat in early May. The set, designated ASV Mark II by the British, was crudely assembled yet devastatingly effective. Each set was light enough to be mounted on a patrol aircraft. The entire apparatus weighed just under 250 kilograms. The transmitter/receiver unit weighed 120 kilograms. The antenna arrays weighed 30 kilograms. The display console weighed 100 kilograms. The antenna arrays defied traditional radio design. A forward-facing array of 3 dipoles was mounted on the nose, while side-facing dipoles were strung under the wings. The set carried no dedicated processor, relying entirely on the operator's interpretation of a green trace on a cathode ray tube. The set's primary advantage was its operating wavelength. Seyss-Inquart examined the transmitter's resonant cavity in the harsh glare of the laboratory lamp. The cavity was tuned to a frequency of 212 megahertz, corresponding to a wavelength of approximately 1.42 meters. 5 years in radio engineering had taught Seyss-Inquart to read these circuits. Every wire might hide a secret. Every solder joint could mark a subtle design innovation. This wavelength was key, long enough to propagate over the vast distances of the Atlantic, yet short enough to reflect sharply off the metallic hull of a U-boat, even one running on the surface with its hatches closed. The hull construction of the U-boat was based on pre-war standards. 2 layers of high-tensile steel plates formed a rigid, pressure-resistant shell that could absorb depths of up to 200 meters. The entire boat required 6 months to build and cost 3 million Reichsmarks. A typical Type 9C U-boat displaced 1,120 tons. Korvettenkapitän Ulrich von Hassel, a veteran U-boat commander who had survived the May massacre, spent 4 weeks in the Berlin laboratory, learning every flaw and strength of the new radar. Von Hassel was a tactical genius who had once commanded the most successful wolf pack in the Battle of the Atlantic. He could diagnose an enemy's tactical intent by the very position of its radar beam. This technology is crude, Von Hassel explained to his fellow officers, but its deployment is genius. Wrong frequency and you'd lose all detection range. Let the planes fly too high and you lose ground clutter. But treat it right and it gives the Allies a 1,000-yard advantage when they need it most. Von Hassel developed a series of evasion maneuvers based on the radar's characteristics. He created a pre-combat checklist that included checking the sea state for maximum wave reflection, ensuring the hull was free of any highly reflective metal, and instructing the watch crew to instantly dive to 10 meters upon the first visual sighting of an aircraft. His analysis would keep U-boats operational when their established operational doctrine said they should have failed. The ASV Mark II, a technical revelation. Admiral Dönitz stood on a makeshift deck built in a testing hangar designed to simulate the bridge of a surfaced U-boat. Dr. Sessincourt guided the Admiral through the technical specifics of the captured set. The core of the set was its power. The ASV Mark II used a pulsed magnetron transmitter, a device that could generate short, intense bursts of power up to 10,000 watts at regular intervals. Imagine a powerful lantern, Her Admiral, Sessincourt explained. But instead of a steady light, it is a flash of lightning, repeated at a rate of 500 times per second. This brief, intense power is what allows the signal to travel so far and return with enough strength to be detected. The detection process was the crucial element. A U-boat, with its large metallic sail and deck, presented a perfect target. A surfaced, stationary U-boat has an approximate radar cross-section of 16 square meters and a detection range of 25,000 yards. A surfaced U-boat, running on diesels, has an approximate radar cross-section of 20 square meters due to increased reflection from exhaust and a detection range of 30,000 yards. A submerged U-boat, at periscope depth, has an approximate radar cross-section of 1 square meter and a detection range of 5,000 yards. The destroyer's main vulnerability was its size and inflexibility. At 388 feet long, the destroyer needed 800 yards to complete a full turn at speed. Her draft of 12 feet limited her to deep water channels. Her 5-inch guns couldn't depress low enough to engage targets closer than 300 yards. Against small, fast targets at close range, the destroyer's advantages evaporated. The key to the ASV Mark II's success against U-boats running on the surface at night lay in the phenomenon of sea clutter. Older radar systems operating on longer wavelengths often had their signals masked by the return echoes from waves. The 1.42-meter wavelength of the ASV Mark II was short enough to minimize this clutter, making the solid metallic echo of a U-boat stand out against the background noise. May 29, 1943, 2300 hours. 4 simulated U-boat models, running on electric motors, idled in the darkness of the testing hangar. Sessincourt observed the display console, which was connected to the captured Allied radar. No radio communication, only the humming of the generators and the faint phosphorescent glow of the display. Von Hassel was next to him, watching and listening. Without a FuMB on the U-boats, they were relying on what sailors called the Mark I eyeball. Human vision, adapted to darkness after hours without artificial light. At 2347, a lookout, positioned on the simulated conning tower, spotted a faint trace on the plane position indicator screen. It was a small bright smudge, the echo of the largest simulated U-boat model. The standard U-boat evasion doctrine called for a rapid crash dive, followed by a sharp course change. But with the element of surprise lost, Von Hassel chose a radical countermeasure: maximum speed on the surface, running directly into the enemy's beam. "The enemy will expect us to dive," Von Hassel explained. "This radar is optimized for surface detection. Diving is slow. If we run at top speed directly at the aircraft, we reduce our reflective cross-section and close the range too quickly for the aircraft to properly align its attack run. The model U-boat increased its speed to 17 knots, closing rapidly on the simulated aircraft position. At 500 yards, the radar echo on the screen became momentarily huge, then disappeared into the central blip of the transmitting aircraft, a phenomenon known as minimum discernible range. The aircraft's bomb bay doors would be opening at this range, but its weapons, the depth charges, could not be accurately aimed at such close quarters without a visual sighting. The second model, simulating an attempted dive, was a catastrophic failure. As the boat began its descent, the change in its angle of reflection created an even stronger, clearer echo on the screen. The dive, which took 25 seconds to reach 20 meters, allowed the simulated aircraft more than enough time for a precise attack. The countermeasures and the consequence. The revelation of the ASV Mark II forced an immediate and complete overhaul of U-boat operational doctrine. The disruption of May 1943 convinced Admiral Dönitz to pull all U-boats from the North Atlantic for a period of 3 months. Additional equipment arrived with new tactics developed through hard-won experience. Intelligence revealed the Allied patrol schedules, runs every 2 to 4 nights, weather permitting. 2 to 4 aircraft per convoy escort group. Route predictable, long sweeping patrols around the Azores and the Bay of Biscay. Corvette and Captain Ernst Lindemann developed new tactical doctrine based on the findings. U-boats would operate in smaller, more dispersed groups. One boat would act as a decoy, generating an electronic signature with its radio antenna, while the others maintained total radio silence and submerged transit. When radar was detected, which happened at least 70% of the time, the decoy would force the aircraft to take evasive action, disrupting the overall patrol pattern. The new focus was on stealth and warning. The FuMB Beobachtungsgerät, or FuMB, was rushed into production. The first model, the Metox, was a crude, hastily built antenna connected to a radio receiver. It could detect the 1.42-meter wavelength of the ASV Mark II out to a range of 10 miles, giving the U-boat commander a precious 10-minute warning to crash dive. 8 U-boats approached the Bay of Biscay in the largest convoy interception run attempted since the May losses. U-boats began their transit using the new Metox sets. Though the boats fired no torpedoes on this patrol, the psychological impact was significant. German reports noted, enemy airborne radar makes surfacing operations extremely hazardous, must maintain constant vigilance for the Metox warning signal. U-511 achieved one of the few tactical victories, using the new doctrine to evade a B-244 Liberator by running at top speed on the surface and then crash diving just as the Metox warning screamed. This demonstrated that U-boats could be effective against a radar-equipped opponent, provided they had adequate warning. Admiral Dönitz, realizing the tactical limitations, personally oversaw the next major technological push. His flagship, the Type 21 U-boat program, was accelerated. This new class of U-boat was designed for vastly improved submerged speed and endurance, allowing the boats to remain underwater for days, effectively negating the airborne radar threat. The Metox was eventually superseded by the far superior FuMB-7 Naxos receiver, which was capable of detecting the newer, more dangerous centimeter wavelength radar. The sinking of Teruzuki marked the peak of PTO anti-destroyer operations. Though PT boats would not sink another Japanese destroyer, their cumulative impact as one element of the broader interdiction campaign was significant. German records revealed the extent of disruption. Airborne radar combined with long-range aircraft makes surface operations increasingly untenable. Operational efficiency reduced below sustainable levels. Admiral Dönitz, after analyzing the data, noted, the enemy's airborne radar, while rarely leading to an immediate kill, forces constant evasive action and submerged running that severely degrades our patrol duration and speed. By January 1944, the U-boat operational strategy shifted almost entirely to snorkel operations and the deep-diving Type 21 program, methods even less efficient than the surface attacks. The combination of airborne radar, Very long-range aircraft and improved surface escorts had made the traditional U-boat wolfpack strategy unsustainable. The U-boat campaign demonstrated that naval warfare had entered a new paradigm where multiple weapon systems working together could neutralize traditional advantages. U-boats alone could not defeat the Allied convoys, but as part of a combined arms approach, they contributed to strategic victory. The captured ASV Mark II set, resting on the table in Berlin, had served as the unexpected catalyst. The German admirals had examined the crude electronics and understood why their U-boats were vanishing. They were not being hunted by superior skill or even superior firepower, but by a ghost in the ether, a silent, invisible beam of energy that had turned the vast protective cloak of the night into a deadly, illuminated trap. The discovery forced the Kriegsmarine to adapt, but adaptation came too late to save the Battle of the Atlantic. The technological race had been lost.